Hi, welcome to my presentation on torque. What is torque, you might ask? Good question. First, let's consider, why do objects move? Objects move when the forces acting upon the object are imbalanced. There could be 1, 2, 3, 4, as many forces you want. As long as the sum of the forces on the object is not zero, the object will begin to accelerate. Let's consider a few situations where forces are at work. First, picture a ball on a slope. There are three forces acting on this ball: force of gravity, force normal, and force of friction. We know from experience that this ball will begin to roll down the hill. The sum of the forces is not equal to zero. Let's picture another scenario. A person is on the top of a cliff. In a sad accident, they fall off the cliff into the water. We understand how the forces work in this one too. Eventually, the person's force of air resistance and force of gravity will even out and reach maximum velocity. Now let's consider a final example. We have a door. Hinges are located on the left side. We push the door. What happens? The forces in this one are a little bit more blurry. When we push the door, it swings outwards. But why? We're used to objects moving in a straight line, not spinning. How do we explain this? The answer is torque. Let's consider another example. I'm making salad for my parents because I really can't cook anything else. I wash up the salad, and now I want to dry it. Picture my salad dryer. Is there some other name for that? I don't know. Well, let's look at a view from the top. This will give us a better idea of what's going on. Our force is applied at the right-hand side of the lever. On the left is our pivot point, indicated by the black arrow. Then we have our lever arm, which we'll mark as R. If there is one thing you are going to remember from this presentation, it's that torque equals R times F sine theta, where R is the distance from the place where the force is applied to the pivot point, and F is the force applied. We include sine theta because torque is the cross product of R and F. This means we only care about the force perpendicular to the lever arm. To take this into account, we include the sine theta. Let's go back to our door example. Let's look at a few different scenarios with the door. Remember, torque equals R times force sine theta. Here's our door. Let's take a look from the top. First, we're going to apply the force at the very far right-hand side at an angle of 90 degrees. We can think of the torque in this situation as being equal to R times F, because sine of 90 equals 1. In our next situation, we can imagine we apply the force in the middle of the door. This will have the torque because 1/2 of its original length. In our final example, we can imagine we're applying a force at an angle. Now, not all of our force is directed in the direction the door will swing. You can imagine this is sort of like pushing the door into the wall instead of pushing it outwards. In our final example, we'll imagine pushing the door exactly at the hinge. Have you ever tried to open a door like this? Not very effective. That's because the torque, or the rotational force, is equal to 0. It's a good thing to remember that any force applied at the pivot point will have no effect on the torque. Now let's talk about equilibrium. We've previously understood equilibrium to be where the sum of the forces equals 0, but now our definition needs to change to include torque. Even though the sum of the forces might be 0, an object still might be able to spin. So, for an object to be in equilibrium, the sum of the forces and the sum of the torques must be equal to 0. Like a lot of other things in physics, the unit for torque is kind of annoying. It's Newton meters, which is the same as joules. However, torque is not measured in joules. This is because a joule is a scalar, and torque is a vector. This is a good time for us to try a practice problem. Let's picture a wheel that is suspended by a washer in the middle. This is a better wheel. Now imagine that we have a stream of water that is pouring on the right side of the wheel. It exerts a constant force water. Let's think about the other forces that are also on the wheel. There's a force of gravity that should be going straight down from the center, and then there's a force normal that's going up from the center. To determine the mystery force that will keep the system in equilibrium, we will write a sum of the torques equation. We will call clockwise positive. Fn and Fg do not figure into the equation because their forces are applied directly at the pivot point. To keep the system in equilibrium, we will apply force push at a distance of 1/2 the radius. So now we can look at our equation just like a sum of the forces. Because the system needs to be in equilibrium, the sum of the torques is equal to 0. Thus, the torque due to Fw is equal to the torque due to Fp. Now let's say that force W is equal to 50 newtons, and that the radius of the circle is equal to 2 meters. Then, the torque, as we know, is R times F sine theta. We can determine that the torque due to Fw will be R2 times F, which is 50. Sine theta will be equal to 1 because the torque is applied directly perpendicular to the lever arm. So our torque due to Fw will be 100 Newton meters. Now you can substitute 100 in for torque due to Fw and solve for torque due to Fp. Since the two are equal to each other, as we determined earlier, torque due to Fp equals 100. Now we know that the force Fp is applied at 1/2 of the radius, so our R is only equal to 1. So to determine our force, we will divide 100 by 1, and we find that Fp is equal to 100 newtons. Yay! Alright, let's move on to a more difficult problem. This is one that's more like what you'll have to solve in class. Imagine we have a beam that's attached on the left end by a hinge and on the right by a string. The length of the beam is L, and the mass is m. Theta is the angle between the beam and the string. Let's draw a free body diagram. X marks the center of mass. The force of gravity is always drawn from the center of mass. This will help us with our torque equations. We want to find the force of the hinge. First, we know that the system has to be in equilibrium because the beam isn't moving. The sum of the torques has to equal 0. And it has to equal 0 no matter where the pivot point is placed. If we put the pivot point at the force of gravity, force tension will try to rotate the beam counterclockwise, so force of hinge must try to rotate it clockwise. Because we know the forces must be balanced, force of hinge must also point to the right. We now know that force of hinge points upwards and to the right, at an angle of what we'll call alpha. I'll draw it in later. Now we want to write our sum of the torques equation. We'll place our pivot point at the far left where the force of hinge is applied, because that's our mystery force. Now let's write our sum of the torques equation using clockwise as positive. Force of gravity will try to spin the rod clockwise, while force of tension will try to spin it counterclockwise. We know that the rod is in equilibrium, so we can set these two equal to each other. Force of gravity is applied at 1/2 of L, and we know that the force of gravity itself is equal to mg. Now let's look at the torque due to force of tension. R in this case is L because the force of tension is applied at the full length of the rod away. We only care about the force that is perpendicular to the lever arm, so we'll have to use sine theta. Since we're trying to find out what the force of hinge is, let's think about how we're going to solve this problem. Our unknowns were force of hinge and force tension. We have now solved for force of tension. Because we know the rod is in equilibrium, we can also use some of the forces to solve our problem. Let's start with the sum of the forces in the x direction. We know that Ft cosine theta, because we're looking at the x, minus Fh cosine alpha is equal to 0. We can express Ft in form of variables that we know. Using some rearranging, let's write an equation for Ft. Hopefully you can see how we've rearranged the torque of force G and the torque of Ft to make an equation for force of tension. Since we know that some of the forces in the x direction are equal to 0, we can set Ft cosine theta equal to Fh cosine alpha and substitute Ft into our equation. Remember that sine over cosine is equal to tangent, so you can rewrite this as mg over 2 tangent theta. This simplifies our equation a bit. Now we have two unknowns in our equation, force of hinge and alpha. Let's look in the y direction. We know that because it's in equilibrium, the sum of the forces in the y must equal 0. Let's call downwards positive. You can write Fg, or mg, minus Ft sine theta minus Fh sine alpha, because we're looking only in the y direction. Our variables are still alpha and FH. Let's rewrite this so we have an expression for FH that we can substitute into some of the forces in the y direction. Remember that Ft equals mg over 2 tangent theta. We now have enough information to solve for alpha, which we can then substitute back into our equation to find force of hinge. Yay! Alright, a few more notes about torque. First off, when we're solving torque equations, remember, if the system is static, as in not moving, you can put the pivot point wherever you want. This allows you to solve with a system of equations. Instead of using forces, you can use torque with the pivot point at the left, right, middle, wherever you want to. However, I kind of lied earlier when I talked about the ball rolling down the hill. It's a little more complicated than it seems. If you want to use torque to solve an equation for a ball rolling down a hill, you need to put the pivot point where the physical pivot point of the ball is. That is, if there's a system that's not static, you can only use one pivot point, in this case, where I've indicated where the ball touches the hill. In situations like this, we'll often use energy instead of multiple torque equations to solve the problem. Alright, that's the end of my presentation. Hopefully I've made torque a little bit less annoying for you.